Hello, everyone. Welcome to tonight's episode of the 101st season of the Watson Lectures at Caltech. Whether you're joining us for the first time or you've been with us all season, we're really glad you're here. And I hope you had a chance to check out some of the pre-game, some music, some drinks, some food, and of course, maybe an up-close sneak peek at some of the technology that Wei Gao, our speaker tonight, is going to be sharing with us. So with the Watson Lectures, we're really trying to open the doors of Caltech both literally and figuratively. And so I want to give a very special welcome to the students of Garfield High School. As members of our junior Watson program, they had a chance to tour Wei Gao's lab. And of course, we told them about all of the opportunities to study science and engineering here at Caltech. So thank you guys so much for coming. I'm Crystal Dilworth. I'm your host for this evening. I'm a science communicator and a Caltech alum. And after getting my PhD in molecular neuroscience here, I moved into a career communicating the connection between fundamental research and our everyday lives. And I think the Watson Lectures is a really unique way to kind of highlight that connection, as you'll see with some of the work that Professor Gao will be presenting. So over the course of this series, we've been talking about the Watson series and exploring a little bit of the history. So in October, we talked about how the lecture series started as the brainchild of Ernest C. Watson. And then last month, we heard Watson in his own words, or at least in a letter that he wrote to the lecture committee, talking about why we do science in the first place. It's just plain fun, if you're not in grad school. Tonight, we're gonna that's the youngest grad student I've ever seen. Tonight, we're going to talk about the history of public science lectures in general. Because at Caltech, we're celebrating a century of these lectures, but institutions like the Royal Institute in London has almost 200 years of presenting science to the public with their public series, the Friday Dialogues. Now, the Friday Dialogues were originally conceived so that they could share and announce new ideas and innovations with a very dedicated public. Over the course of the more than 3,000 Friday Dialogues, we've seen Faraday introduce the first photograph. We've seen Thomson introduce the concept of the electron. Maxwell proved Faraday's theory of lines and force. And Swan showed a brand new innovation, the incandescent light bulb. Now, the Friday lecture series in the Royal Institute was focused on the ideas and the innovations. But I hope that you guys agree with me that scientists deserve to be seen as people too. So tonight, we're going to hear a little bit about Wei Gao, the person. So before his talk on biosensors and the future of personalized medicine, you'll hear an introduction from the chair of the Division of Engineering and Applied Sciences, and then a short video about Wei Gao's life and work. Then after his talk, you guys get a chance to ask your questions. So remember what they are. And then you'll see a QR code on the screen, which will send you to Slido, which is the way that you can submit your questions with your phone. If you're old school, we've got some ushers in the back that have comment cards, and they'll help you write them down and make sure that they're uploaded so that I see them so that we can ask Professor Gao. And of course, afterwards, as usual, there's tea and coffee and continued conversation, and possibly some one-on-one time with Professor Gao outside. So we hope that you stick around for that. Okay, I think that's all the business. So if you guys will take this opportunity to silence your cell phones, turn off your watches, all of that tech that beeps, check your nearest exit just in case, you never know what's going to happen, and allow me to introduce the chair of the Division of Engineering and Applied Sciences, Professor Harry Atwater.
Good evening, and welcome to the Watson Lectures in person. We're delighted to have you all here. And we're very excited to hear the work and the stories and the exciting results from tonight's speaker, Wei Gao, who's going to tell us about work at the interface of wearable biosensors and personalized medicine. So let's think a little bit about this subject. In 1990, the Department of Energy launched an effort called the Human Genome Project to sequence the human genome for the very first time. That project wound up with sequencing the first human genome after about 10 years, a decade of effort, in the year 2000, and spent about $3 billion doing that to sequence the first human genome. And of course, what happened after that was that technology and innovation powered a revolution such that today it is possible to sequence the genome of a human, any human, in about 24 hours, and the cost has gone down from that first cost of the first sequencing from $100 million down to about $1,000. And that's the power of technology and innovation. And today, we're going to hear about how technology and innovation are powering a new revolution using wearable devices that will usher in and harbor a new era of personalized medicine. And we're extremely excited to hear Wei Gao, who is on the forefront of and leading efforts in this revolution, to tell us about those advances tonight. Wei earned his PhD in chemical engineering from the University of California, San Diego in 2014. And he served as a postdoc at UC Berkeley until 2017 when he joined the faculty at Caltech. And his development in his group has followed that same sort of Moore's law progression that the entire field of genomics and now wearables has followed. And he's he's an assistant professor of medical engineering, Heritage Medical Research Institute, Ronald and JoAnne Willens Scholar. He's the recipient of many awards. He's the associate editor of Science Advances, which is a very prominent journal in the field covering all fields of science. Has many awards. I won't list them all here, but among them the NSF Career and ONR Young Investigator Award. He was named by MIT Technology Review as one of the 35 innovators under 35. And most notably, he is, this year in 2023, a highly cited researcher. This is something that academics pay very close attention to, from the Web of Science. And not only that, this is the 5th year in a row that he has been accorded and noted with this honor. So it's my pleasure to introduce Wei Gao, who's going to tell us about skin-interfaced wearable biosensors.
Caltech campus is very beautiful, peaceful. I enjoy time to work in my office as well. At Caltech, I was inspired to think big, to explore new things, to develop a really novel technology that could benefit human health. I'm Wei Gao, assistant professor of medical engineering at Caltech. My lab is developing different types of bioelectronic devices for personalized and precision healthcare. I was born in a small village in China. From my education, from my parents, I learned that being a scientist or engineer was a way to change my life. Actually, my interest in biomedical engineering started from the time my grandma passed away because of stroke as late diagnosis. So I was thinking if I could develop technology that could give people early warning or could cure the disease, that's one of the main motivations to me, for me to become a biomedical engineer. I came to the United States in 2009. Certainly there are a lot of challenges, culture difference, language barriers, how people work in the lab. It took a year for me to get used to it. I get my degrees from mechanical engineering, chemical engineering, and did my postdoc in electrical engineering. So I started to think, what if we could collect chemical molecular information from our daily activities continuously and non-invasively? This could be very helpful to get more comprehensive information about our health. By analyzing human sweat using wearable sensor, we could collect a large set of information that could be used for health monitoring, disease diagnosis, and very importantly, the information could give us early warning for preventive care. My team is highly interdisciplinary. Many of my group members are developing novel sensors. They develop, test, and characterize different types of electrochemical sensors in the lab. We prepare our wearable sensors on plastic substrates such as PET and polyimide. So we can 3D printing, inkjet printing, or laser engraving our sensors on such disposable, low-cost plastic substrate. My favorite part of my job is interacting with the students. Chat with them about the progress, discuss the challenges they face in their research. I'm always impressed by my students' dedication and innovations. In the past Halloween, actually, my students surprised me a lot. They all wear white or blue shirts with jeans. They try to cosplay another Wei Gao. Then we have like over 30 Wei Gao standing in front of me, and I was really surprised. There are a lot of clinically relevant biomarkers in our sweat: hormones, peptides, and proteins. We can only detect a few right now. I wish we could develop a novel biosensors that could monitor these biomarkers toward different types of health conditions such as cancers. We hope one day in the near future, our sensor can be worn by many people and provide real-time information about our metabolic, inflammatory, and mental health conditions. Looking at the future, we should be able to identify all the health conditions at an early stage, and we can perform timely intervention, and we could live healthier in general. Good evening, everyone. Welcome to JoAnne. And today is such wonderful for me to have this opportunity to share our recent research. I'm Wei Gao. I'm currently assistant professor of medical engineering. And the Gao lab at Caltech Medical Engineering is highly interdisciplinary, and our lab is focusing on material, device, and system innovations for translational medicine. In today's lecture, I will firstly introduce the motivation and the background of our research. Then we discuss the main challenges existing in this field. Then I will talk more about in the past 6 years how our lab is trying to address these challenges. Finally, I will give an outlook and perspective. As we know, wearables can play a very important role in personalized healthcare because they can continuously collect data from our body and tell us what's going on and what's going wrong with our health. But if you look at all these commercially available health monitors, like Apple Watch or Fitbit, so they can mainly track the physical activities or vital signs, but cannot provide more useful information about our health at molecular level. We think a major gap, which is also a great opportunity in the field of wearable sensors, is how can we perform physiological monitoring at molecular level, ideally continuously and non-invasively. If we think of what are available right now for continuous molecular sensing, we know there are CGMs, continuous glucose monitor. But again, they are still invasive and are only limited to monitor glucose right now. Thinking of non-invasive molecular sensing, we are looking at one important body fluid, human sweat. Essentially, we are sweating all the time. Sweat is a very important body fluid we can retrieve conveniently, continuously, and non-invasively. Sweat contains a number of different types of biomarkers or analytes, including a variety of electrolytes, metabolites, and over 30 amino acids, over 300 proteins, and many other peptides, hormones, and substances such as drugs and heavy metals. Imagine that if we could develop a wearable platform, we can wear this like wearing our Apple Watch or Fitbit. We can continuously collect this chemical or molecular information from our daily activities. We could use this information for health monitoring, for disease diagnosis, and very importantly, this will give us early warning before we develop more severe health conditions for preventive care. Another very important direction is The large sets of chemical molecular information are not available right now. If we couple this data collection with the existing vital sign or physical data collection, coupled with machine learning AI, we could enable numerous fundamental and clinical investigations, especially toward biomarker discovery. So I published my first work back to 2016, while I was still a postdoc at UC Berkeley. So we introduced a fully integrated wearable sensor that can perform multiplex in situ sweat analysis. So this wearable device can monitor glucose, lactate, sodium, potassium, and the skin temperature. It is a wireless system that can perform on-site signal conditioning, processing, and data collection. We also developed a cell phone app. You can real-time check the biomarker or analyze information or concentration from your phone. You can also always send the data to the computer through email or upload data to the cloud. Already close to 80 years. So this work has been cited already close to 4,000 times. You can imagine many experts around the world are working in this field right now. Tremendous progress have been made in this field as well. But again, there are still major challenges in this field to realize full potential of this wearable biosensor or wearable chemical sensor. So here, I listed 5. I will briefly introduce these challenges, then we will discuss how we address these challenges from our research. Firstly, we need to mass produce this high-performance chemical sensor at low cost. Why? Because these chemical sensors, they are not like a pacemaker, which can be used for 10 years. Even CGM, continuous glucose monitor, people invest billions of dollars. Right now, you can use it for 2 weeks, 4 weeks. You still need to replace a new sensor after usage. So we are thinking we need to prepare sensor at low cost so people can afford it. People can use it in their daily activity. And second challenge is, since we are doing sweat sensor, I always face this question: what if I don't have sweat? Right? Typically, we do exercise, we have sweat. When the weather is very hot, we have sweat. But again, there are many times you don't feel you're sweating while you are. But the problem is we need to address this challenge. If we want to apply this to broad population, for example, for patients, they cannot even do vigorous exercise, right? How can we get sweat? And how can we sample sweat? In this case, can we monitor our sweat 24/7, for example? This is the next challenge. Access sweat across activities and efficiently sample sweat to get real-time sweat analysis. The third one is really, there are so many biomarkers. The majority of clinically relevant biomarkers, actually, they are present in our body fluid, including sweat, at very low concentration. It's very hard to detect them in situ, automatically on the skin. We know in a laboratory test, you can run a lot of benchtop operation to detect some target biomarker accurately. But again, that's not practical in daily activity, right? For usage in daily activity, right? So this is the third challenge. We need novel sensing strategies to monitor clinically relevant biomarker at extremely low concentration from the skin. The fourth one is really, we are developing technology. We need to show they are useful. We need to validate the wearable technology in healthy people, in patient population, to really show they can be very useful for disease prevention or management. Last but not least, we are living in a sustainable world. We try to build a sustainable world. Sustainable wearable operation need a sustainable wearable power supply. How can we power our future wearable sensor? Can we even not using any battery to power our wearable sensing? This is our last challenge I want to talk. So from the following slides, I will introduce our recent works, try to address this challenge one by one. Of course, we're not fully there yet, but we are on the way. So firstly, to mass produce this high-performance sensor at large scale and low cost, we are initially started to use laser engraving. Laser engraving is a very interesting approach. We are using CO2 laser. We can directly pattern this beautiful graphene structure on the surface of plastic polyimide. Because of photothermal process, essentially, is laser is burning the surface of polyimide and cause localized carbonization. This 3D graphite graphene composite can be readily prepared simply using laser engraving on the surface of plastic. We can control the laser parameter In this case, we can make these graphene structures that are very suitable for high-performance chemical sensing. You see that for this laser-engraved graphene electrode, they show much higher or better performance compared to other commercially available electrodes, including glass carbon electrode, gold electrode, or screen-printed electrode. We can also tune the laser parameter to prepare graphene structures that are suitable for physical sensing, to monitor vital signs such as respiration rate, heart rate, or temperature. So moreover, we could use laser engraving to pattern microfluidics. You may ask why I need microfluidics. Because we are doing sweat analysis. People always ask, what if sweat evaporates? Right? Can you still accurately analyze sweat? What if when new sweat come out, it will mix with old sweat? Right? How to address this problem? Microfluidic is a solution. So we put a sensor inside these microfluidics. When sweat come out, the new sweat will push away the old sweat. Our sensor will always analyze fresh sweat. And because all the sensing is done in the microfluidics, and we have miniaturized influence from evaporation. So overall, high-performance chemical sensors, physical sensors, and microfluidics can be entirely prepared using laser engraving. Basically, using laser coupled with plastic. You can imagine, could be very large scale and low cost. Our lab's first graduate student, Isabella, actually, she received Forbes 30 under 30 in science because of this work. Of course, our approach is not limited to laser engraving. We could use other approaches, such as printing, for example, inkjet printing. We know that we use inkjet printer in the office to print our papers. But again, can we print the sensors? This would be a very interesting approach as well. Instead of using commercially available color inks, we can prepare our own nanomaterial inks. Why we need a different type of nanomaterial? Because a certain material may be preferred to detect a certain type of compound because of the unique physical and chemical property. So we can custom design our own inks, for example, prepare our own silver nanoparticle ink, carbon nanotube ink, graphene oxide ink, and silver nanowire, MOF, Maxine, all these nanomaterial inks we can prepare in the lab. Just by programming from the computer, we can directly print a different material at different location to fabricate physical sensor, chemical sensor, overall multimodal sensing. We can entirely prepare using simple printing in this case. We have applied this physical chemical sensor for human-machine interaction. We could also apply this approach to prepare wearable physical and chemical sensors at larger scale and very low cost. The third approach for mass production of this chemical sensor or physical sensor in general is 3D printing. Recently, 3D printing is attracting a lot of attention because it is very suitable for prototyping in a source-limited environment. For example, we could possibly use a 3D printer to print different things at home. So in this case, we have developed our own, again, inks so that we can 3D print different modules of this wearable sensor, including high-performance physical sensor to monitor temperature, to monitor pulse waveform, respiration. We can print microfluidics for sweat sampling. We can also print chemical sensors entirely using automatic 3D printing. Moreover, we can print energy storage devices such as micro-supercapacitors. Overall, all the main modules of this wearable sensor can be 3D printed. So very convenient, we can make this type of devices in the laboratory or in a home setting. So, okay, I've showed you some applications, actually some approaches, 3 approaches already to mass produce these low-cost biosensors. So in the next slide, I will show you how can we get a sweat. I mentioned it earlier. We need to address this challenge to make sure our device can be used by most people. How can we get a sweat without need for any vigorous exercise? So we actually learned from the literature that there is a process called iontophoresis that can be used to locally induce sweat. This is used actually in a clinical setting for cystic fibrosis diagnosis. Cystic fibrosis is a genetic lung disease. Actually, clinically, people use sweat tests. The doctors will use this FDA-approved device to induce sweat. How can it induce sweat? Basically, we are applying a small current, 1 to 1.5 milliampere. We deliver a positively charged drug molecule, pyrocarbon molecule, below the skin, which will bind to sweat gland, trigger localized sweating. Actually, using this approach, sweat will automatically come out after stimulation. So the doctors will use this sweat collector to collect sweat, then send out to a lab to do chloride analysis. Again, this is for cystic fibrosis diagnosis. So inspired by this approach, we're thinking, can we have a miniaturized iontophoresis module on our wearable device so that anytime we can get a sweat without need for exercise, right? So here, we develop our next generation of wearable sensor. It is a wearable platform that can autonomously induce sweat across the activity. We only need to apply here a very tiny current, much smaller, 20 times smaller than commercially available devices, actually. 50 microampere. Actually, as a user, you will not even feel anything. We only need to apply 5 to 10 minutes, only several minutes. You don't need to apply current anymore, and sweat will continuously come out because we transdermally deliver a drug called carbachol, which will bind to sweat gland, have long-lasting effect, trigger localized sweating. With several minute stimulation, you will actually have sweat from this small area for a few days, at least for several hours. It works on me for 2 days. You get only from this small area, continuous sweating. Again, you don't need to apply current anymore. You only need to apply a few minutes. It's not like we always apply current to stimulate the skin. Just one time, you get several hours to several days of sweating. Of course, you can restart this process whenever you want. So this is a highly attractive approach. This allows us to get a sweat and sample sweat at any given time. So here I have a video to show you how sweat come out and how get refreshed. So we use black dye in the middle. You see, let's say this is old sweat. When new sweat come out, the black dye will get pushed out to the outlet because sweat gland is an automatic pump. It will pump out new sweat and push away old sweat. So our sensor is actually sitting in the middle reservoir. We always analyze fresh sweat. So, well, this is already an attractive approach, allow us to get sweat across activity. We could apply this for a number of applications, right? You don't need to ask people, do some exercise for me to get sweat, let me put a sensor on you. We don't need that. So that's why from following slide, I will show you how we apply this approach, our sweat sensor in this case, for different type of biomedical applications. Firstly, we have shown we can apply this to monitor gout by non-invasively continuously monitor a key gout biomarker, uric acid. Gout is the inflammatory arthritis affecting tens of millions of people around the world. My brother has gout as well. As a gout patient, it's quite painful if they like to eat red meat, shellfish, or drinking beer, because this too high pure diet intake will increase uric acid in the body, and uric acid will crystallize near the joint, triggering tremendous pain. It is very helpful for the patient if they could monitor uric acid so that they can change their lifestyle to minimize chance for developing gout. It is also very helpful for the gout patient to monitor uric acid so that they can, personalize the diet to avoid the gout attack or flare up. And for the patients who are on medication, many gout patients eat medications such as allopurinol to control their uric acid level. It's like a diabetes patient using insulin to control glucose level. So monitor uric acid will be very helpful for them to personalize the drug dose. So in collaboration with the UCLA Medical Center, Dr. JoAnne Lee, in particular, Dr. Lee is the chief of clinical nutrition at the UCLA Medical Center. We actually recruited a lot of subjects, including healthy subjects. You see that for the healthy subject, after overnight fasting, uric acid levels are both low in sweat and serum. After we give our subject a pure-enriched diet, which is a kind of sardine, many people don't like sardine, but we did it this way. You can see uric acid increase substantially after pure-enriched diet intake from male and female subject. We actually recruited a patient with gout, also subject with hyperuricemia. We found that for patients with gout, their sweat uric acid and blood uric acid are both much higher compared to healthy people. If we track one subject over 7 hours, you see that sweat uric acid follow very closely the serum one. So we get a correlation factor, in this case, actually 0.864. It's pretty good, simply putting all the data together. If we could introduce more individual calibration mechanism, we could potentially get a much higher correlation factor. Right now, supported by NIH, we are doing a clinical trial. We are planning to recruit 100 to 200 gout patients at UCLA to evaluate whether this approach can be really used to improve gout management and drug adherence. And what we are interested in not only monitor uric acid, even uric acid is very important for gut, it's also a risk factor for cardiovascular disease, renal disease, and even diabetes. But again, our body contains so many different types of circulating metabolites and nutrients, which play a very important role in body function. For example, we have 9 essential amino acids in our body. They are called essential amino acids because they are essential to our body. So how to monitor? If we could monitor this amino acid or vitamins using wearable sensor, this will be very important to realize precision nutrition to let us live longer, live healthier. So, but again, developing such nutrient sensor is not straightforward as developing a glucose sensor, which you can find an enzyme called glucose oxidase very selectively. They can catalyze the reaction of glucose, right? In this case, it's very challenging. So to address this question, we actually developed a new universal sensing strategy based on molecularly imprinted polymers, which work as an artificial antibody. How we can prepare this? This bioreceptor, we call it artificial antibody because we can prepare the polymer by polymerizing monomer and target molecule together so that the polymer will be formed with the target molecule inside. After we remove the target molecule from the polymer will contain cavities. The cavities will have the same shape and size as the target molecule so that they can recognize the very selectively target molecule back again. The mechanism of shape recognition is also similar to antibody-recognized protein because of shape recognition is the one major aspect of selectivity. So we have this polymer, they are selective to target already. We can develop different polymer selective to different target. And we can build a sensor on our laser-engraved graphene electrode, which give us pretty high surface area and good electrochemical performance. Between the polymer and graphene, we are introducing a redox probe film, actually a chemical with a redox signal, such as Prussian blue or methylene blue. Why we need this? Because the target bound to the polymer is selective, but again, they don't give us measurable signal. How can we quantify the recognition? We are incorporating this redox film. When the target bound to the polymer, actually redox film signal will be influenced because this target filled the cavity. The exposure of the redox probe to the sweat media, sweat matrix will be affected. By quantifying the redox probe signal, we can actually quantify different type of circulating metabolite nutrient. Using this approach, we could realize continuous monitoring of every single type of essential amino acid and many other vitamins, lipids, and drugs. So this is a very interesting approach, and actually what we are interested in, not only monitor the micromolar level circulating metabolites and nutrients, we know that there are a lot of clinically relevant biomarkers. They are proteins and hormones. They are well known in the clinical setting, very meaningful for disease management, but again, they are present in our body fluid at so low in concentration, actually nanomolar, picomolar, or even lower. It is very hard to detect this type of compound. How can we realize automatic sensing of such extremely low-level biomarkers? I would like to share 2 approaches. Firstly, we are using antibody as a recognition element. Antibody can recognize target. For example, in the first example, I will show you how we can detect C-reactive protein. It is an inflammatory biomarker. CRP is a well-known biomarker for systemic inflammation, and inflammation is associated with many major leading causes of death, including heart failure, including COPD, infections such as sepsis and COVID-19. If we could monitor inflammation remotely at home, this could be life-saving. For example, COPD, the main reason for the death is because of COPD exacerbation. It is reflected by inflammation. That's why it is very important to have such a tool to allow the patient or high-risk population to monitor inflammation. But again, CRP is a large protein, relatively large molecule, and it's very hard to come out through sweat gland, and they are only present in our sweat at a few picomolar level. How to detect such protein from the skin? We introduced a new sensing approach here based on antibody. It's based on sandwich assay. So we use 2 antibodies. One is called a capture antibody. We can immobilize the capture antibody on the surface of the protein, on the surface of like a graphene. And the other antibody is called detect antibody. So we actually capture antibody, we immobilize on the electrode of graphene. For the detect antibody, we are linked linking this detected antibody to a gold nanoparticle for signal amplification. We are leaving the gold nanoparticle with antibody in the microfluidics. You see how we develop this wireless system. Firstly, we have this fully integrated system. You can control sweat induction. Basically, by clicking a button from the phone, you can trigger localized sweating. When sweat comes out, CRP will come out from skin. And CRP will go through, sweat will go through microfluidic, CRP will bind to the detected antibody, and the continuous sweat flow will bring all the reagent on the top of working electrode. Then CRP bind to the capture antibody, so we form this sandwich assay. Continuous sweat flow will rinse away all the excess amount of reagent. Eventually, only clean sweat is left in the sensing reservoir. So we can detect how much CRP on the electrode by detecting a redox molecules, which we conjugated on the detector antibody. We are using thionin, a molecule which gives us a redox signal. By quantifying how much thionin on the working electrode, we can back calculate how much CRP. It is an automatic process, allow us to detect CRP from the skin. And we actually incorporated additional sensors, including pH sensor, ionic strength sensor, and temperature sensor. Because people may argue, what if this person's sweat or the other person's sweat have different composition? What if every day my sweat also fluctuates, pH and salt? We have this real-time multiplex sensing and perform real-time calibration to get a high accurate in situ on-body sensing. So we get a pretty good sensing result, and we have evaluated this sensor on different type of human subjects, including healthy people, non-smoker, smoker, COPD subject, heart failure subject, and subject with infection, as well as subject recovered from COVID-19. We have observed increased CRP level in both blood and sweat in smokers and in patients with all these major health conditions. And we get a pretty good correlation between sweat and serum CRP. The correlation factor is 0.84 here. And again, for CRP, people with systemic inflammation, the CRP could change dramatically. Look at this one for infection. This is the patient data. The dotted line are data from healthy subject. CRP could change by several times to even 100 times. With this correlation, we can say that this device could be used for remote systemic inflammation, could give people early warning when they have this infection. You should come to the clinic, see the doctor in general. So another very important application I want to show you is how to detect a very low concentration of hormone in using another sensing approach. Here we are choosing another very important clinically relevant hormone, female hormone estradiol. You know, female hormone is very important, play a very important role in women's health. For example, estradiol, it is crucial to monitor ovulation. This could be very important for fertility management, tell us what time ovulation comes. Right now, for fertility management, you have to, if you want to know the time, you can buy a temperature sensor from Amazon. You know, temperature sensor is not accurate. It's a much delayed result. Having this will give us early sign about ovulation. And more crucially, I would say, estradiol plays a very important role in menopause. It causes all the problems like mental health for women as well. If we could have this technology, we can remotely monitor estradiol at home at any time. This would be very important as well. But estradiol also only present in our body fluid at the picomolar level, very low in concentration. So here we are using a different bioreceptor, aptamer. Aptamer is also working as an artificial antibody. And actually, we immobilize the aptamer on one electrode. We can let aptamer bind to a single-strand DNA, which is linked to a redox probe, which gives us measurable signal. When the electrode is present, is immersed in sweat, estradiol will bind to the aptamer because aptamer will because of competitive bonding, aptamer will prefer bond to the estradiol. Then kick off this single-strand DNA. Then single-strand DNA will migrate or diffuse to another close by working electrode. Here, it's actually printed a MAXine gold nanoparticle electrode modified with single-strand DNA with complementary sequence to this diffused single-strand DNA. The hybridization of DNA will make the redox probe get closer to the working electrode. In this case, we can also detect redox probe changes so that we can convert back to the estradiol concentration. Why we design so complicated way, in a complicated way? Because it is crucial to reach high sensitivity, low detection limit. Why? Because when we don't have estradiol in sweat, no signal can be detected from working electrode. Even there is a small estradiol in sweat, we can still detect a small increase of the signal from working electrode. It's much easier to detect 0.1 change from background from 0 compared to detect 1 change of 1 from a fluctuating background of 100. The crucial for high sensitivity here is low background signal, low blank signal. We actually designed a smart ring. You can wear this like wearing a ring or a bandage. You can perform autonomous sweat induction, sampling, and real-time estradiol analysis. We also incorporated pH, temperature, and ionic strength sensors to do the real-time calibration to make sure we can get accurate result of estradiol from skin. We actually incorporated another design here, capillary bursting valve. Why we need this design in the microfluidics? Because we want to sample a fixed amount of sweat. So when sweat come out, it will enter the microfluidics. When the microfluidics get filled, because of the capillary effect, the new sweat will not enter this reservoir anymore. We will directly flow out. So in this case, we only sample a fixed amount of sweat in the beginning. Then incubation and detection are both performed in a quiescent solution. In this case, give us high sensitivity and stability of the sensor in general. So we apply this approach to monitor the estradiol from our women subject. We did actually 2 months continuous monitoring. You can see that the cycles, the fluctuation of estradiol during the menstrual cycles over 2 months. We get a pretty good correlation between sweat and blood female hormone level. So this is, you can imagine, this is very important for fertility management and menopause management. Okay, I've showed you 2 approaches. How can we detect protein? How can we detect hormone at a very low concentration, few picomolar level? In the following slides, I will show you another very important application of this wearable sensor, using this wearable sensor for monitor stress and mental health. Stress is very important. It's associated with over 90 or even 95% of diseases, including cancers, cardiovascular disease, diabetes, and depression, PTSD, and so on. Even stress is so important. It is very hard to quantify. Right now, the gold standard is based on questionnaires. You get asked a bunch of questions. Based on your answer, a score will be generated. You can imagine this could be very subjective. Similarly, pain is also based on questionnaire. Depression diagnosis is also based on questionnaire. And even suicide, my psychologist collaborator was telling me, it is also based on questionnaire. You can imagine in many cases you will not get the answer you desire, the accurate answer. Our goal is if we could build a tool that can work like a temperature sensor that can quantify stress accurately. So we are looking at initially, what are the important stress biomarkers? One of the most well-known stress biomarkers is stress hormone cortisol. Cortisol is a well-known stress biomarker. When our body experiences stress, cortisol level increase rapidly in our body. And we could possibly quantify cortisol and evaluate the stress in this case, right? But again, another question is, if you draw blood to monitor blood cortisol, this is problematic. Because blood draw itself induces a lot of stress. So make your measurement problematic, right? That's why non-invasive stress hormone sensing is very important. So we developed this wearable sweat sensor that can quantify cortisol from skin wirelessly within 1 and 1.5 minutes. So this could be very interesting already. And we actually did a lot of tests in our lab, for example, cold pressure test. You just need, for me, actually, I need to put my hand. I was the first subject in my lab to do this research. At that time, I have to put my hand into ice water. Guess what I feel? A lot of pain, because this cold pressure test is a pain test. At that time, when I realized, feel pain, I noticed that all my lab members are staring at me, make me even more stressful. Then I realized why you are looking at me, because later on I know that everyone put $1. They just bet how long their advisor can keep their hand in ice water. So it was a very nice experience, and I couldn't bring my hand out, because if I do so, nobody will do this study later on, So we did a pretty good trial later on. We found a pretty good correlation between sweat and the blood cortisol level. Right now, we are working on developing more stress hormone sensors to quantify stress in general. But again, it is very challenging to detect very low concentration stress biomarker. Then another also question coming into our mind, even though the biomarker is associated with stress, even when we have stress, this biomarker level increase. But how do I know the exact stress right now, stress level, right? So actually, then we think about, okay, what if we put all the stress-related biomarkers together, we develop a sensor array that can quantify all these important stress-related biomarkers? Stress response is affecting many parts of our body, influencing our metabolism, influencing cardiac activity, influencing our immune response as well. So actually, for example, glucose is a very important stress biomarker. You might not know, even you don't take any food or sugar, if you experience stress, your glucose level, blood glucose level increase very quickly. It is a very good stress biomarker. And skin conductance is also a very important stress biomarker. By incorporating all these important stress-relevant biomarker sensors in the same patch, we develop this wearable sensor that can simultaneously monitor 6 chemical biomarkers and 3 physical biomarkers. 3 physical ones including temperature, including skin conductance, and our pulse waveform. You can extract heart rate variability, and possibly blood pressure from this information. And how we can quantify stress in this case? We design different type of study. We let our subject experience different type of stressors. For example, do vigorous exercise, cold pressure test, even playing VR game to induce stress to our subjects. Then we collect all this multimodal data from all different type of activities. We even did a real-time stress monitoring test. Eventually, we have this physical, chemical information, multimodal information. We can run machine learning using AI to help us decode the links between these biomarkers and the stress levels. Using this machine learning, we can classify with very high accuracy different type of stressors and different levels of stress. We can tell our stress level with a confidence level of over 98.7%. Pretty accurate. We are actually working closely with the US NASA, US Navy, and US Army because stress is also associated with the human performance. This will be very important to optimize the training of these, let's say, warfighters, astronauts, and also will be very important to monitor overall the long-term stress level influence to mental health down the road. So the last part of my talk, I want to introduce another important challenge I mentioned, how we address this challenge. How can we power future wearables? I've showed you many applications. Most of these prototypes, we are using a small lithium battery. Of course, nowadays, we can always recharge our battery if we run out of electricity. But again, not all the time you can find the power source. For example, in a source-limited environment in developing country, or when you're performing tasks in the rural area, in the desert, in the forest, or in many other places, you couldn't find the rechargeable electricity available. How you can power future wearables? We think a major attractive aspect of future wearable from power aspect, if they could harvest energy from the human body or from the environment, this would be very helpful. Since we are doing sweat sensor, we are thinking, can we use sweat to power our sweat sensor? Because we are sweating essentially anyway. Sweat contains a lot of chemicals. What if we can convert the chemicals in human sweat into power? In this case, we introduced our solution. Here, a biofuel cell-powered electronic skin or wearable sensor. Here, we are using biofuel cell. It is an enzymatic biofuel cell based on lactic oxidase that can catalyze chemical reaction of the lactate. So basically, it can convert lactic acid in human sweat into electricity. Actually, our sweat contains pretty high lactic acid level, from 5 millimolar to all the way 60 millimolar. Very high. It is wasted anyway. What if we convert this chemical into electricity, right? We designed the biofuel cell so efficient that we can realize the first time a battery-free wearable system that can still perform multiplex sensing, signal processing, and Bluetooth-based wireless communication. Again, not using any battery. How we can realize that? We are here using different type of nanomaterial on the bioanode. We are using from 0D to 3D nanomaterial to increase the surface area and the electrochemical activity of this biofuel cell. We can actually get up to 3.6 milliwatt per centimeter square from untreated human sweat. It's continuous power, pretty high already. Even when the subject contains low lactic acid level, we can still get 2 milliwatt per centimeter square. This allows us to demonstrate a battery-free system that can continuously monitor different type of markers. As exemplar, we showed here, we can monitor ammonia, urea, temperature, glucose, and pH. Battery-free system. So in collaboration with another Caltech professor, Professor Zita Imami, actually, Professor Imami is an IC design expert. She designed this integrated circuit chip, very small, as you can see, 1.06 by 1.32, for power management. So after integrating with our biofuel cell, overall system is still very small, 5.5 by 6.2 millimeter for power management in general. Right now, we have new chip, actually just did a tap out. We can incorporate 15 to 20 sensor channel into the same chip in this case for signal processing part. For power management, signal processing on the same chip. As you can imagine, our future or next generation of this wearable sensor could be much smaller in this case. Not only we can get energy from biofuel cell, from sweat, another source is from the environment. We know light is available everywhere. We are thinking, can we get energy from ambient light? In this case, we are demonstrating a light-powered wearable sensor using perovskite solar cell. We actually have this flexible solar cell that can convert available light, not only outdoor but also indoor, to electricity to power entire wearable system. We're talking with our team from the beginning. We want a system work even under weak indoor light. You don't have to stand under California sunlight outside on a hot day, right? Office light, will that be enough or not? That's why we use the perovskite solar cell, which have pretty high power conversion efficiency under weak indoor light. This allows us to power entire wearable system using this miniaturized solar cell and electronic system. This can power not only sensors, but also iontophoresis. Firstly, we power the iontophoresis module to induce sweat locally. Then when we have sweat, we can have this sensor to monitor sodium, glucose, for example, and sweat rate. We can power amperometric sensor, potentiometric sensor, impedometric sensor, and voltammetric sensor, all different types of electrochemical sensing modality we can power using this battery-free system. So we have demonstrated that we can continuously monitor all these markers using exemplar pH, glucose, sodium, and sweat rate. In the dietary challenge, you see that even sweat glucose, for example, follow very closely the blood one. We can track all these biomarkers during daily activity. We demonstrated we could continuously monitor this from actually for 12 hours in this case. We can do outdoor activity. We can also do indoor activity under different type of illumination conditions. You might argue, what if at night there's no light, right? Of course, for this demonstration, we showed a battery-free system. You can always put a very tiny battery. During the day, the sunlight will power everything, or room light will power everything. That can also charge the small battery. We also show that with this tiny battery, even entire night operation without light, the battery voltage can remain very stable. That means we probably don't need to charge this wearable system ever again if we use this solar cell. We should also, this one solar cell could work for several months, can still power the entire system. So last but not least, our lab is not only working on wearable sweat sensor, we are also working on a number of other wearable sensors. For example, we have this smart bandage developed to monitor chronic wound. So we have developed this wireless system that can perform multiplex wound biomarker monitoring. Wound is affecting a lot of people right now. Diabetic ulcer, venous wound, they are creating a staggering, financial burden for our healthcare system in general. So we could wirelessly monitor a number of wound biomarkers, including uric acid, glucose, pH, ammonia, as well as lactate. Not only they can do multiplex sensing to let us learn more on the microenvironment, they can also do combination therapy. They can deliver drug, for example, to treat an infection. We can deliver anti-inflammatory and antimicrobial drug through the built-in hydrogel on the sensor patch. They can also do electrical stimulation for tissue regeneration. So overall, including monitoring and combination therapy on the same patch. You see, very small. We have evaluated this patch in small animal model, including mice and rats. And very recently, we evaluated a newer version of this platform in human subjects for patients with diabetic ulcer and venous wound. To conclude my talk today, I've introduced you a wearable platform that could enable continuous non-invasive data collection from our daily activity. This large set of chemical or molecular informations are not previously accessible. If we couple this with existing physical or vital sign monitors, we could have this multimodal data collected during our daily life. We could use this coupled with data mining, machine learning, big data right now. This will be able to enable numerous fundamental and clinical investigations, and we are looking at the future of biomarker discovery. We can associate, dissociate, and decode all the biomarker information with specific health conditions. In the end, I would like to thank my wonderful group. Many are in the audience. They did most of the work through their innovation and hard work. I would like to thank many of our clinical collaborators for evaluating our technology, and many of engineers and scientists at Caltech and other institutes for technology development. Finally, our funding support. Thank you very much for your attention.
Thank you so much, Wei. All right, it's now time for you guys to ask your questions. So get those phones out, send some good ones, and if you want to have a seat, we can get started. Wei, you described your research as interdisciplinary, and you were not kidding. You showed a staggering variety of expertise in these projects that you presented. For someone that might want to work in a lab or work on projects like this, what would be your recommendation for? What should they study? What should you, grow your expertise in?
I think, my group is highly interdisciplinary. We have students from background with background from chemistry, material science, electrical engineering, biomedical engineering. And right now, we have more like people working heavily on the data analysis, machine learning. I would say for the students who study for graduate school, even for college, it is very important for you to have high interest and high interest in a particular topic, because many things you can learn from your research later on and build a solid background on one aspect at least. Right? So you can really make major contribution either from chemistry, material system, and of course, during the research, you can learn other aspects as well. Nobody can do everything. It's always a collaborative work. I think have really good knowledge on one aspect and try to learn others.
Yeah, I think that's a really important point, that science as an activity is highly collaborative, so you don't have to know everything.
That's right. I don't know many things. I have to learn a lot from my students as well. Yeah.
As usual, we have a question about when will these wonderful innovations be available commercially? So which one of the projects is, more commercially developed, and what goes into kind of getting this from slides in a lab to actual people?
Yeah, in today's talk, I've already highlighted the major challenges before preventing us to develop a commercially viable product. Recently, we have made a lot of progress. We think it become more and more close to real-life applications. And actually, we are also working with our tech transfer office to try to commercialize our technology. I would say, I hope in the next several years, we will see some product on our wearable biosensors.
What does it feel like to wear one?
I would say we start with the prototype with a wire connection. Right now, we do all the wireless. I think you actually don't feel you're wearing something in many times, because it's more like you're wearing a bandage. It's fully wireless, and even electrical stimulation with such a small current, you don't even feel anything. So we try to really create a product, let the user feel very convenient, comfortable, not feel troublesome while wearing this. Yeah, you could envision you're wearing a bandage.
Like a Band-Aid.
That's right.
I see. So there's a question here about how immediate is the reporting of sweat in terms of what the inner state of the body is. So what is, for instance, in stress, What is the time period between feeling stress and being able to detect via sweat?
Yes, that's a very good question, actually. Certainly, chemicals in human sweat, their concentration will have some delay compared to blood. Similarly, people do CG, continuous glucose monitor. People found there are several minutes for interstitial glucose, their delay compared to blood. We also observe the same. I would say at a level of several minutes, the chemicals in sweat will reflect the blood ones. But again, for most of these applications, we think this is already pretty good for remote health monitoring.
So minutes.
Yes, several minutes, yes.
There's also a question about whether there's any key biomarkers where sweat concentration and serum concentration are not highly correlated. So are there strategies for getting around this, and what are those biomarkers?
Yeah, that's also a very good question. Not everything in sweat correlates with blood, actually. We found, for example, actually sodium, chloride, lactate, they have no good correlation with blood. But we also observed many biomarkers. Today I showed, many hormone, proteins, small molecules like nutrients. They have very good correlation with blood. I think partially because of the secretion mechanism. If it is based on diffusion from blood, we tend to find a pretty good correlation. Of course, this requires more knowledge about sweat physiology. And again, because of lack of literature, in many of our research, we actually try to investigate initially, do they have a tentative correlation or not? And the study of the correlation is part of our research as well. Okay. Yeah, that's why many correlation, for example, take one example, estradiol, the female hormone project. Before our research, there was actually no literature showing female hormone is present in human sweat. We have to spend a lot of effort and time to identify whether they are in our sweat, or what is the concentration. Then we develop a sensor to monitor this in situ and build a correlation to study the correlation.
I see.
Yeah.
As a neuroscientist, I really like this next question, which is, we've talked a lot about being able to detect signals that are coming from the body. What about being able to inject signal back into the body using this type of wearable technology?
Yeah, that is another very interesting topic. We already inject something. Think about the way we induce sweat. It is transdermally deliver drugs or molecules such as acetylcholine, such as carbachol, like a transdermal drug delivery. It is possible to incorporate such mechanism, but of course, there is also other approach we could apply for the electric stimulation from the skin to give people some feedback. Similarly, even for the wound study, we even did electric stimulation for tissue regeneration. But I think more feedback mechanisms such as electric stimulation or transdermal molecular drug delivery would be possible to incorporate together with the sensors.
I see. So the answer is yes, we can,
Yes.
and we're doing it.
That's right.
Excellent. You showed a few options, but is there a best place on the body for this type of wearable?
Yeah, so actually, we did most of our study in forearm, in the wrist part, just because we think very important form factor would be more like a watch, like a device, or incorporating with one of the smart watches existing. So, but we also tried to study at different years, actually, at different part of the body. We studied the back, arm, and the chest, and even forehead, We found that if we do stimulation, actually, there is the composition may not change much, actually, at different locations. But of course, for given individual, we try to do the study at a similar location so that we can get more consistent results.
So I guess some of the things would just be what's comfortable for the wearer.
That's right. That's right. We think the arm or the wrist is somewhere people often wear things that would be more convenient other than stick in the chest or in the back. But it's possible also. Sweat gland also secrete properly in those locations. We can apply this like a bandage in different body parts.
So you showed a little bit of this, but can you talk a little bit more about how advances in AI are really influencing the design and the application of these technologies?
Yeah, as I said, so our research actually enables continuous, non-invasive chemical or molecular data collection. While currently there are a lot of AI-related research, a lot of wearable technology, mostly based on skin conductance, temperature, pulse waveform. Even that could be powerful for some applications, but overall applications are still very limited because only from physical parameters we get, not comprehensive information. Right now, our strength is we can couple physical and chemical together to collect multimodal information. In this case, we can get more comprehensive knowledge or information from our body. In this case, when we couple this with AI, with machine learning, we showed that for stress, for example, we can get high accuracy for classifying stress types and stress levels. Yeah, that's not everything could be beneficial, but when we have large set of data, we can figure out what are the most relevant biomarkers. For example, when we design a patch for stress or for other application, we firstly choose what are the relevant biomarkers. Maybe in the literature report, we know that stress affects heart rate, affects temperature, affects our glucose level, or even hormone level. Can we develop a sensor to incorporate all the choice to do investigation? Through machine learning, we will figure out what are the important choice of markers. Maybe we don't need so many. Eventually, maybe 3 or 4 or even 2 could reflect accurate result already. This is part of investigation. Help us really decode the association of this biomarker or body parameter with a specific health condition.
So right now, it's helping you identify the best targets.
That's right, best target and what we can get from target, yeah, how accurate we can predict different health conditions, yeah.
There's a great question here about how do you know that the induced sweat is chemically similar to natural sweat?
Yeah, that's a very good question. You know, we learned from literature that why we are sweating. So for example, our body similarly regulated sweat. When we feel hot, this sympathetic neuron near our sweat gland, we will secrete molecules such as acetylcholine. Acetylcholine bound to the muscarinic receptor, which will control the ion transport. This is how we are sweating, naturally. So actually, stimulated sweat is a very similar process. Instead of let our neurons secrete acetylcholine, we transdermally deliver acetylcholine or similar chemicals. So they will also bind to the muscarinic receptor, trigger localized sweating. So essentially, from physiological point of view, it's a very similar process.
Okay, so we think it's the same.
Not necessarily exactly the same, but it's very similar, I would say, yeah. Because we could also, our body, like a neuron secrete acetylcholine, we can also transdermally deliver acetylcholine. Just we found the carbacle works even better in case of long-lasting sweat, yeah.
I see.
Actually, this type of sweat is actually, we think has more advantages because it's more controllable, allows us to get steady sweating locally throughout the activity. For example, if we do vigorous exercise, our body changes very quickly. It's very hard for us to study the correlation between sweat and body biomarker. But with stimulated sweat, we steadily sweat for a very long time. It's very good for such correlation investigation and overall even continuous monitoring for machine learning driven different type of applications.
How do things like temperature and pH affect the measurement of these biomarkers?
Yeah, so because most of our sensors, they are based on electrochemical sensor. For example, enzymatic reaction like glucose sensor. The enzymatic reaction will be influenced by temperature and pH. So because such influence, we need to consider we are doing directly on the skin. We are not testing in the standard buffer solution. We are doing in standard, on the skin. And everybody's sweat composition may be different. pH, temperature, ionic strength. That's why we are trying to incorporate these sensors to real-time quantify what is the current pH, ionic strength, and temperature, and we can real-time calibrate the sensor to get a very accurate in situ sensing result.
That sounds complicated. Real-time calibration scares me.
Our goal in general, try to make the engineering part complicated. We consider all the factors so that the user, they do minimal thing. They place the patch on, you can directly read from the phone. Yeah.
How long do these sensors last?
That is also a good question. It depends. Depending on sensors, for example, our ionic strength sensor, to monitor ions, we showed that the sensor could last for several months, actually. For the enzymatic sensors, such as glucose, lactate, uric acid sensor, in a recent effort, we showed that they could work very stably for several days in sweat, for 4 or 5 days, which, for some sensors, of course, they're only one-time use because of the detection limit. So overall, that's one of the reasons why initially from my lecture, I showed that we need to mass produce these sensors at large scale and low cost. So that every day, every several days or every week, you can easily replace the sensor patch within a few seconds while you're charging your watch or wristband, for example. Yeah, larger scale, low cost, mega sensor, disposable. Because even we try our best, even like CGM, you still need to replace periodically.
There's a collection of questions here around ability to predict episodes, for instance, like schizophrenic episodes or depressive episodes, or predicting the onset of a condition. Are we able to do that, and how would we go about solving that problem?
Yeah, so I mean, certainly we haven't done that part, but we are on the way. It's one quick example is really, for example, stress monitoring, right? We are on the way to using our multiple students working on stress-related project to get real-time information. Then from the phone, you can get a feedback. What is the current condition right now? What is the stress level right now? You can give people early warning and real-time feedback. That is the purpose for doing real-time monitoring. And there are so many problems we want to go, but of course, challenge is really we try to build sensors that can quantify more biomarkers relevant. And we then try to make all the sensors more and more stable so that we can trust the data collected from daily activity. Then with all the data, we can do the on-site monitoring, give people early warning, real-time feedback. Yeah.
What is your hope for this technology? How do you want to see it impact humanity?
I really hope people could have this, through our technology, we want to show they are useful, and people could really have this at home, and in time, depending people which disease people at risk, they can monitor this remotely, so that they can learn better about their health status, they can adjust their own lifestyle, for example, or the doctors will get more feedback or information, give people early warning and really let people live healthier, not developing major health condition. That's the main application of motivation, prevention, give people predictive, warning in general.
Well, I have to say that your talk has given me hope that we'll be able to catch things early and have better preventative care in the future. So thank you for adding that optimism to this evening.
Thank you, everyone.
There were lots of other questions, so if you didn't get your question answered, please feel free to join us for tea and coffee and additional conversation with Dr. Gao. And thank you so much for coming. Make sure you register for January's Watson lecture. It's going to be amazing. We have Bethany Ellman coming to speak to us. So hopefully I'll see you in January, and everyone have a wonderful evening.